Welcome back to our Chapter 4 lecture on Engineering Economics with Statistics and Probability. In order to proceed with our discussion on inferential statistics, we're going to look at two different methods of inferential statistics. The first is point estimation, and the second is hypothesis testing. Point estimation allows us to predict what variables are going to be best representations from a population for a certain statistic. Point estimation is going to allow us to approximate a value from a population just given a statistic. It'll also allow us to somewhat measure the accuracy or the estimation of our value. Hypothesis testing will then allow us to go on and predict outcomes of certain statistical tests or of a system. It will also allow us to measure how well our hypothesis matched our result. So compare what we were predicting to what actually happened. We'll get to this in our next video. There's a lot of new jargon and Greek letters that go along with point estimation, so let's take a minute to go over some of those. First of all, there's a parameter. A parameter is some characteristic of a population which is represented as the Greek letter theta. A statistic, which is represented by the capital Greek letter theta with the hat, is some characteristic of a sample that we are using as an estimate of a parameter. So a way to look at this and remember is that populations have parameters, samples have statistics. So it's alliterative: population, parameter, sample, statistic. So the last word we're going to talk about is our new word, which is point estimate. All that is it's a number, which we're going to represent with a theta hat, that is considered to be our best guess or our most plausible value of an actual parameter. So we will do a bunch of examples to try and get to know these best, but basically what we care about is we have some value from my sample, which is a statistic, that the actual value of that statistic is my point estimate, and we are then going to use that point estimate to predict a value from a larger group known as a population. Let's get into some of my common point estimates for parameters. So for my population mean, so remember what we're going to do is we're going to have some value that's going to predict or estimate my population value. So I'm going to use X bar as my sample statistic that's going to represent my population parameter mu. So the reason all these values have these little hats on top or the caret on top of them is because they denote a guess. They denote that we are estimating. So by this being written this way, we are saying we are using X bar to approximate my mu. So mu hat means an approximated or an estimated value. So then our population variance, we would have S squared, which is my sample variance, which would then predict my sigma squared. Okay, so population proportion, which is one thing relative to another, we would have just my number divided by my sample size. That all would then predict my p hat or my proportion hat. The difference of my means would then be approximated using the difference between my x bars, and that would then be used to predict the difference in my mu's or my mu hats. And then proportion difference, once again, we would just use our x's to predict my p's. There is a more comprehensive list in your book on page 151. That table will also list the given formulas for each of these if you need them. Okay, so let's go on to look at an example for all of these words. So we're asked to determine the average lifetime of a specific type of ballpoint pen. Since we're asked to find the average, we will find the mean sample statistic, so X bar, and use it to approximate the mean population parameter, which is mu hat. So once again, we are going to predict mu hat with X bar, and the value I get for X bar would then be called my point estimate. So the reason I'm doing this, let's think about this just for a second. Why can't I just write with every single pen forever and figure out what the average is? Well, there's a couple reasons. One, it would take a lot of time to use every single pen created by some company until it runs out of ink. And the other problem with that theory is that if we used all of the pens until they ran out of ink, we wouldn't have any more pens left. So we're just going to take a sample of these pens, find the average of how long their lifetime is, meaning how long until they run out of ink, and then we will use that to predict how long all pens will last until they run out of ink. So the way we're going to go about this is we're going to have some machine write with a pen until it runs out of ink, and they will clock that data. So here we have data from this said machine. So we have these values listed of how many hours a pen can write before it runs out of ink. So I calculate my average of all those values just by adding them up and dividing them by n, and I get x bar equals 28.5. So 28.5 is now my point estimate. So my sample statistic, or the description of my sample that I care about, is my x bar, or my mean, and the value for that is 28.5, and I would then use that to represent my population parameter of mu hat, or my average population parameter. I hope that helps clarify things a little bit. So now let's get into characterizing point estimators. So ideally, a point estimator, or my theta hat, capital theta hat, would give us an accurate estimate such that it equaled the true population parameter. So in an ideal world, I want everything I test from my sample to equal my population parameter. However, that's not always the case. In practice, a point estimator may give different values for different samples. So how do we know which point estimate is the best one? How do we know which one to choose? So we can characterize our point estimators in terms of two different properties. One being bias, which describes how close my sample statistic is to my population parameter, or how far apart they are from each other. The other is variance, and variance describes how spread out my data is, or how far away from my mean it is. Okay, so let's get into bias. Given some population parameter theta, a point estimator is called unbiased, or an unbiased estimator, if my expected value of my statistic equals my population parameter. So if what I am predicting equals my population parameter, or if my statistic equals my population parameter, then it's called unbiased. So if they're equal to each other, then it's unbiased. However, if they do not equal each other, then they are called bias. So a bias of a point estimate is defined as follows. So we say the bias equals the difference between my expected value and my population parameter. So once again, if my statistic, or if what I'm predicting, equals my parameter, then it's an unbiased estimator. If they're different, then we figure out how different they are, or the difference between the two, and that equals my bias. Okay, so note here in this equation that the bias can either be a positive value or a negative value. All it would tell you that the sample statistic was to the left of the mean or the right of the mean. Okay, let's look at an example with this. Let's let x1, x2, x3, and so on denote a random sample from a population having a mean mu and a variance sigma squared. Consider the following estimators of mu. So I'm going to say that statistic 1, or capital theta hat, equals all of these values added up and divided by 9. And then statistic 2 equals a combination of them. So we're going to say 3 times x1 minus x sub 6 plus 2 times x, all divided by 2. So these are random samples. So we want to know, is either of these estimates unbiased? So the way we figure that out is we're going to calculate our expected value. And is that equal to my population parameter mu? So it tells us we have a mean equal to mu. So we need to figure out if it equals mu or not. So let's solve this. So I'm going to say the expected value of my first statistic is going to equal 1/9 times each of my expected values of these different variables. So all I did was evaluate each expected value at its given variable. Okay, so I simplify that, and then that turns into 1/9 times 9 times mu, and that gives me mu. So I just calculated that my expected value equals mu. So since I know that this equals mu, or that it's equal to my population parameter, then it is an unbiased estimate, because the expected value equals the true mean mu. So let's look at the other one. So if I say the expected value of my second statistic, that's going to equal 1/2 times the following. So once again, all I did was I evaluated the expected value at each variable. So I'm simplifying this. I plug in mu for the expected value, and that simplifies to be 2 times mu. So what I'm saying is my expected value ended up equaling 2 times my population parameter, or 2 times my population average. So that's not what we want. So that then would be a biased estimate because the expected values are not equivalent to the true mean. Now let's get into standard error. Given a point estimator, or capital theta hat, the variance of the point estimator is denoted by this. So the variance here would just equal sigma squared over n. So we talked about this formula before with sampling distribution. It's kind of the same concept where we now have a distribution of many different samples and their point estimates. Okay, so my standard error this time is just the square root of my variance. So standard error is just the standard deviation of these point estimates. So sigma over the square root of n. So note here that the variance of the point estimator may be calculated using estimated values, in which case the error is referred to as the estimated standard error. So that's why we care about the standard errors, that it incorporates the fact that these are estimated values. So this is also important because if we have multiple point estimators with different variances, then variance now allows us to further characterize which one is better. So let's look into that. Given 2 unbiased point estimators, theta hat 1 and theta hat 2, the estimator with the smallest variance is called the minimum variance unbiased estimator, or the MVUE. So this is often referred to by statisticians because we care which one has the smallest variance. The point estimator with the smallest variance is the one that you're going to want to choose to represent your population. The MVUE is the one most likely to produce a point estimate equal to the actual value, and the MVUE is also important when it comes to distributions. It's been shown that for a normal distribution, the sample mean is your MVUE. So that kind of saves you the step with a normal distribution of having to guess, do I use the median, do I use the standard deviation, do I use the mean? So with a normal distribution, your sample mean is going to be your MVUE. So in practice, an unbiased estimator is not always available. So when we use a bias estimator, it's useful to be able to characterize the error associated with the point estimate. So there are different types of errors associated with biased point estimates as well. So we have the standard error and the mean square error. So the standard error once again is going to come from my variance, and the mean square error, however, this time now incorporates my bias into it. So my mean square error, or my MSE, provides a measure of the variance and the bias of a given point estimator. So how close it is to my mean and how spread out the data is. So my MSE of my statistic equals the difference between my population value and my statistic, quantity squared, or more simply put, we just have the variance plus my bias squared. So keep in mind that the MSE of an unbiased estimator is just the variance, because this value right here would just be equal to 0 if it is unbiased. So if it's biased, however, then you have to incorporate that value into your equation. So we can use the MSE to compare the performance between different estimators in terms of the relative efficiency. So basically, we're going to take the error of one, so the MSE of one statistic, over the MSE of the other statistic, and that will be called my efficiency. So in general, if my efficiency, or this ratio of the two, we call it a relative efficiency because it's one relative to the other. If the relative efficiency is less than 1, then we're going to want to use the statistic in the numerator, because then that would infer that that variance or that value is smaller. If it is greater than 1, then you would want to use the 1 in the denominator. You can remember all of that, or you can just remember you're going to want to use the one with the smaller mean square error. Okay, so note that if it is unbiased, then my efficiency would just be equal to the variance of one divided by the variance of the other, because we don't have to incorporate bias. So this is a nice shortcut if you have an unbiased estimator. Okay, let's look at how efficiency works in an example. Suppose that theta hat 1 and theta hat 2 are unbiased estimators of the parameter theta. We know that the variance of 1 equals 10 and the variance of the second equals 4. Calculate the relative efficiency of the two estimators. Based on your answer, which estimator is better? Okay, so let's first calculate my efficiency. So my efficiency is just 10, so the variance of the first divided by the variance of the second. And notice here we just have a 0 because these are both unbiased, so there's no bias to incorporate. Okay, so that then simplifies to be 5/2. So here the relative efficiency is greater than 1, so we would take the value in the denominator, or we would take the smaller variant. Another way to just look at this would be to take the smaller variance of the two. In general, we always want to take the value with the smaller variance because that means that my values are not spread out as far as they could be, that my point estimates are relatively close to one another, so that helps us predict for our population parameters because they're all relatively equal to one another. So another way to say that is that my estimator 2, or my second statistic, would be a better option since it has the smaller variance. Let's look at one more example incorporating our mean square error. So there's a program called Minitab out there that's a statistical program where you can pretty much put in any statistical problem or statistical question into it, and it will pump out an array of numbers or an array of answers for you. So here, this is a Minitab output, and it tells you a bunch of information. So it tells you that I have a random variable x, a sample size 16, a mean that I'm supposed to calculate, a standard error of the mean, which is 0.159, and a standard deviation that I also have to solve, and the sum of 399.851. So once again, we're supposed to calculate the missing values. So I have an n equal to 16, a standard error of the mean, which is 0.159, and a sum equal to 399.851. So it's up to you to remember what sum means. It's just the summation of each of my individual values. So that's what sum would equal. So my mean would just be my sum divided by my sample size. So my mean would then be 24.991. I would then find my standard deviation using my standard error of the mean formula. So I would just plug in my standard error of my mean, the square root of my sample size, and that would give me my standard deviation. So I'd solve that, and that would give me 0.636. So this is it for this part of Chapter 4. I hope you are a little more clear on point estimations.